Integration by the method of inspection. Okay, so let's begin with the method of integration by inspection. As you know, we've been learning about integration, and there are various techniques to tackle different types of integrals. This method, inspection, is a really useful and intuitive one to start with. Now, the slide title says Integration by the method of inspection. What does inspection mean in mathematics? Well, it simply means looking closely at something. In this case, we're looking closely at the function we want to integrate, that s called the integrand. The first bullet point tells us that this is an intuitive approach. That means it relies more on understanding why integration works, rather than just memorizing formulas. We want you to develop a feel for the process. Instead of immediately reaching for a formula, we encourage you to inspect the integrand and try to remember a derivative that looks similar. Think about what function, when differentiated, would give you something close to what you see inside the integral. Remember, integration is the opposite or inverse of differentiation. So, if you can find a function, let's call it f of x, such that its derivative is equal to the function you're trying to integrate, which we'll call f of x. Then the integral of f of x is simply f of x, plus a constant. See, we'll talk more about that constant later, but it's crucial to remember it. Think of it like this. Imagine you're given a puzzle piece, the result of a differentiation. Your job is to figure out what the original puzzle looked like, the original function. That's essentially what we're doing with integration by inspection. In the next slides, we'll walk through some examples to show you exactly how this works in practice. We'll start with trigonometric functions, then move on to exponential functions, and so on. So, keep this introduction in mind as we move forward, and you'll see how powerful and straightforward this method can be. The logical process. Okay, so now that we've discussed what the method of inspection is, essentially reverse differentiation, let's look at how to actually apply it. This slide outlines a logical, step-by-step process to help you systematically tackle integration problems using this method. First, we have analyzed the integrand. This means carefully looking at the function you're trying to integrate, which we typically denote as f of x. You need to get a feel for what type of function it is. Is it a trigonometric function like sine or cosine? Is it an exponential function involving e? Or is it an algebraic function with polynomials? Identifying the structure is the first crucial step. Next is recall a related derivative. This is where your knowledge of differentiation really comes into play. You need to think, what function, let's call it f of x, when I differentiate it, would give me something similar to f of x, the function I'm trying to integrate? Don't worry if it's not an exact match at this stage, we'll address that in the next step. Now adjust the constant. This is a very common step where students sometimes make mistakes. Often, the derivative of the function you recalled won't be exactly the same as the integrand. It might differ by a constant factor. For example, the derivative might have a 2 multiplied to it, while your integrand doesn't. In such cases, you need to manipulate the equation, usually by multiplying or dividing by a constant, to ensure the derivative you found perfectly matches the integrand. Once you've successfully adjusted the constant, you can formulate the integral. This is the exciting part. If you've correctly identified a function whose derivative is the integrand, then you've essentially completed the integration. You've found the antiderivative. Finally, and this is extremely important, add the constant of integration. Remember that the derivative of any constant is 0. This means there are infinitely many functions that have the same derivative. To account for all these possibilities, we always add an arbitrary constant, denoted by c, to our integral. This represents the family of all possible antiderivatives. We'll see this process in action with some examples on the next slides, starting with a trigonometric function. But keep these 5 steps in mind, and you'll be well on your way to mastering integration by inspection. Illustrative examples, trigonometric function. Okay, let's move on to our first example of integration by inspection. As we discussed in the previous slides, this method is all about recognizing derivatives and working backwards. Here on slide 3, we're going to find the integral of cosine of 2x, written as integral cosine 2x dx, using the method of inspection. Let's break it down step by step. Step 1. Identify the integrand. This is simply recognizing what function we're trying to integrate. In this case, our function, which we call the integrand, is f of x equals cosine 2x. It's important to clearly identify this before we proceed. Step 2. Recall a related derivative. Now, we need to think about what function, when differentiated, would give us something close to cosine 2x. Remember our differentiation rules. We know that the derivative with respect to x of sine 2x is equal to 2 times cosine 2x, so d by dx of sine 2x equals 2 cosine 2x. Step 3. Adjust the constant. Now, this is a crucial step. Notice that the derivative we found, 2 cosine 2x, isn't exactly the same as our integrand, cosine 2x. It has a constant factor of 2. To make them match, we need to adjust. We can do this by dividing both sides of the derivative equation by 2. This gives us cosine 2x equals 1/2 times the derivative of sine 2x, or cosine 2x equals 1/2 times d by dx of sine 2x. Essentially, we're isolating the integrand within the derivative. Step 4. Integrate. Now the magic happens. Since we've successfully expressed our integrand, cosine 2x, as a constant multiplied by the derivative of another function, we can now integrate. Because the integral of a derivative simply returns the original function, the integral of cosine 2x is 1/2 sine 2x, plus our constant of integration, see so, integral cosine 2x dx equals 1/2 sine 2x plus c. Remember, the constant of integration, c, is essential because the derivative of any constant is 0. We've covered this in previous lessons. This example demonstrates how we can use our knowledge of derivatives to inspect the integrand and find its corresponding integral. We'll see another example on the next slide with an exponential function, and then we'll discuss some common mistakes to avoid. Illustrative examples, exponential function. Okay, let's move on to our second example, and this one involves an exponential function. As you can see on the slide, we want to find the integral of e to the power of 5x with respect to x, written as integral e to the power of 5x dx, using the method of inspection. Remember, we're trying to work backwards from a derivative to find the original function. Step 1. Identify the integrand. This is a straightforward step. The function inside the integral, the one we're trying to integrate, is simply e to the power of 5x. We denote this as f of x equals e to the power of 5x. Step 2. Recall a related derivative. Now, let's think about what we know about derivatives. We know that if we differentiate e to the power of 5x, we get 5 times e to the power of 5x. So, d by dx of e to the power of 5x equals 5e to the power of 5x. It's crucial to recall these standard derivatives. Step 3. Adjust the constant. Here's where the inspection part really comes into play. Notice that our integrand, which is e to the power of 5x, isn't quite the same as the derivative we just recalled, which was 5 times e to the power of 5x. We need to adjust things to make them match. To do that, we divide the derivative by 5. This gives us e to the power of 5x equals 1/5 times the derivative of e to the power of 5x. Essentially, we're saying that e to the power of 5x is 1/5 of the rate of change of e to the power of 5x. Step 4. Integrate. Now that we've expressed our integrand as a constant times the derivative of a function, integrating is easy. Since the integral of a derivative simply gives us back the original function, the integral of e to the power of 5x is 1/5 e to the power of 5x, plus our constant of integration. See so, the integral of e to the power of 5x dx equals 1/5 e to the power of 5x plus c. And that's it. We've successfully integrated an exponential function using the method of inspection. Remember, always double-check your answer by differentiating it. If you differentiate 1/5 e to the power of 5x plus c, you should get back to our original integrand, e to the power of 5x. This will confirm that our inspection was correct. In the next slide, we'll look at a real-world analogy to help solidify this concept. Real-world analogy. Imagine you are a detective at a crime scene. You find a specific footprint, and we're going to think of that footprint as representing the derivative, the result of differentiation. Your job as the detective is to determine who the person is, and this who represents the original function, the one we're trying to find through integration, who left that footprint. Now you know that a person of a certain height and shoe size, think of this as our function, f of x, always leaves that specific footprint. The height and shoe size define the footprint. By carefully inspecting the footprint, examining its details, and matching it to a known person in your database, which is essentially your knowledge of derivatives and functions, you can identify the original source, the person who made it. Okay, let's move on to a real-world analogy to help solidify our understanding of integration by inspection. This analogy highlights the core idea of integration by inspection. We're given the result, the derivative, the footprint, and we're working backwards to find the original, the function, the person. Remember, we've already discussed how to adjust for any constant factors, just like how different people might press harder or softer when making a footprint. This will become easier as we practice and build up our database of known derivatives, just like a detective becomes better at identifying footprints with experience. And in the next slide, we'll cover some common pitfalls to avoid, so you don't fall into any detective traps. Common mistakes to avoid. Okay, let's move on to slide 6. This slide highlights some common mistakes students make when applying the method of inspection, or really, when integrating in general. Paying attention to these will save you a lot of points on your exams. First, it says, forgetting the constant of integration. This is extremely common. Remember, integration is the inverse of differentiation. And what happens when you differentiate a constant? It becomes 0. That means there are infinitely many functions that could have the same derivative. To account for all of those possibilities, we always add plus c, the constant of integration, to our answer. So, no matter what integral you calculate, don't forget that plus c at the end. Next, we have ignoring the constant factor. Let's look at an example. It states a common incorrect answer for the integral of cosine of 2x, written as integral cosine 2x dx, is simply sine of 2x plus c. Now, let's think back to our differentiation rules. What is the derivative of sine of 2x? Well, it's 2 times cosine of 2x, not just cosine of 2x. So, to get the correct answer, you need to account for that factor of 2. The correct integral is 1/2 sine of 2x plus c. The key takeaway here is always verify your answer by differentiating it. If you differentiate 1/2 sine of 2x plus c, you'll get back to cosine of 2x, confirming you've done it correctly. Finally, sign errors. This one trips up a lot of students with trigonometric functions. Remember that the derivative of cosine of x is negative sine of x, so when you're integrating sine of x, the answer is negative cosine of x plus c. It's easy to forget that negative sign, so be extra careful when dealing with sine and cosine. These are simple things to avoid, but they can make a big difference in your accuracy. Now, let's move on to the final slide, where we'll summarize the key takeaways from this entire lesson. Key takeaways. Okay, let's wrap up our discussion on integration by inspection with these key takeaways. First, and most importantly, remember that inverse nature. This entire method of inspection relies on understanding that integration is simply the reverse process of differentiation. We're essentially undoing what differentiation does. Think back to how we found the integral in our examples. We were always looking for a function whose derivative matched what was inside the integral sign. Next, verification. Always check your work. The absolute best way to confirm if your inspection was correct is to differentiate the answer you obtained. If you differentiate your result and you end up exactly back at the original function you were integrating, the integrand, then you know you've done it right. It's like a self-check to ensure you haven't made any mistakes along the way. Now, pattern recognition. The more you practice and become familiar with standard derivatives, the quicker and more intuitive this method will become. You'll start to recognize patterns and immediately see the function that will give you the desired derivative. It's like building a mental library of derivatives, making the inspection process much faster. Remember those trigonometric and exponential functions we worked with? The more you see those, the easier it gets. Finally, let's state the general rule formally. If the derivative of a function f of x, that's written as d over dx of f of x, is equal to a function f of x, then the integral of f of x is simply f of x plus the constant of integration. See, so mathematically it looks like this. If d over dx of x equals f of x, then the integral of f of x dx equals f of x plus c. Don't forget that plus c. It's crucial because of the constant term in the antiderivative. So, to reiterate, keep in mind the inverse relationship, verify your answers by differentiating, practice to improve your pattern recognition, and always remember that general rule. With these points in mind, you'll be well on your way to mastering integration by inspection.